Imagine you have a piece of jewelry made of silver, and through some strange molecular magic, you could simply dip it into a solution and swap every single silver atom for gold. In the world of organic chemistry, we have a tool that does something remarkably similar with halogens. It's called the Finkelstein reaction. At its surface, the reaction seems almost too simple. We take an alkyl chloride or bromide. Let's visualize a carbon chain with a chlorine atom hanging off the end, and we react it with sodium iodide. The result? The chlorine and iodine simply trade places. But if you look at a periodic table, you might notice a problem. Iodine is less electronegative than chlorine. In the world of chemistry, the stronger element usually displaces the weaker one. So why would a chlorine atom ever give up its seat for a bulky, less electronegative iodine atom? Let's look at the mechanism to see what's actually happening behind the scenes. This reaction follows an SN2 pathway. Picture our alkyl halide floating in a beaker of acetone. The iodide ion acts like a silent transition state ninja. It approaches the carbon atom from the backside, exactly 180 degrees opposite the chlorine atom. Notice how as the iodide begins to form a bond with the carbon, the bond between the carbon and the chlorine begins to stretch and weaken. For a fleeting moment, we have this high-energy transition state where the carbon is partially bonded to both halogens. Then, in one fluid motion, the chlorine is pushed off entirely. It's a complete inversion of configuration. Think of it like an umbrella blowing inside out in a strong wind. But this still doesn't explain the why. If the reaction can go forward, why doesn't the displaced chloride ion just turn around and attack the iodine to flip it back? In a normal environment, it would. The reaction would just reach an equilibrium and sit there. And here's the key insight. The magic trick of the Finkelstein reaction isn't actually the chemistry, it's the solubility. As you can see here, we perform this reaction in acetone. Sodium iodide is incredibly soluble in acetone, so there are plenty of iodide ions floating around ready to attack. However, sodium chloride and sodium bromide, the byproducts of our swap, are almost completely insoluble in acetone. Watch what happens as the reaction proceeds. As soon as a chlorine atom is kicked off, it finds a sodium ion and immediately precipitates out of the solution as a solid salt. It literally falls to the bottom of the flask. Because that chlorine is now trapped in a solid crystal, it's no longer available to attack the carbon and reverse the reaction. By using a simple trick of solubility, we've effectively tilted the scales of the universe. According to Le Chatelier's principle, by constantly removing the product from the equation, we force the reaction to keep moving forward until every last chloride has been swapped for an iodide. So, the Finkelstein reaction is more than just a substitution. It's a masterclass in how chemists use the physical environment to cheat the laws of equilibrium. It reminds us that sometimes the secret to changing a molecule isn't just about what you put into the solution, but about what you force to fall out of it.